and welcome back. My name is Mr. Kovald, and in this video, I'm going to show you how to find the equilibrium constant from given standard free energy changes of a reaction. So in this problem, we're going to use some tabulated free energies of formation to calculate the equilibrium constant of a particular reaction. So the reaction we're going to be working with is the N2O4 gas in equilibrium with 2NO2 gas. And so we know that from our previous video that when we have delta G, our equation for delta G under non-standard conditions is equal to the delta G under standard conditions plus the ideal rate law constant in terms of joules per mole Kelvin multiplied by the temperature and then ln of Q. So that is the equation. But if we're at equilibrium, we know that Q is equal to K, right? And therefore, the standard free energy or the free energy here is going to end up being zero. So the non-standard free energy change of a reaction will end up being zero at equilibrium. So when this becomes zero, right? So if this becomes zero, then we solve this equation. We get the standard free energy change of the reaction equal to negative RT ln of K. Since we're assuming we're at equilibrium, Q becomes K, and so now we're going to use this equation to help us find the equilibrium constant for this reaction. And we're going to do that by using our tabulated free energy changes, standard free energy changes of formation for the products and reactants. So we're going to start with this equation. So we're going to use, so the delta G, standard free energy change of a reaction, is equal to the sum of the products multiplied by their coefficients. So this is going to be the standard free energy changes of formation of products minus the sum or the addition together of the adding together of the reactants multiplied by their coefficients. So this is going to be free energy change of formation of reactants. So products minus reactants. So we only have one product, so that's going to be NO2. So 2 here is our N value. We're going to multiply 2 by the standard free energy change of formation of NO2, which we have here, 51.3. So 51.3 kilojoules per mole. So we're going to have that written down. So that's 51.3 kilojoules per mole. And the moles, this represents 2 moles here. So moles are going to end up canceling out. And then we're going to subtract that from the reactants. Again, we only have one reactant, so that's easy. And this is a 1 here. So we're going to put 1 for N. And then the free energy change of formation for N2O4 is 99.8 kilojoules per mole. So we're going to put 99.8 kilojoules per mole. And then all we have to do is multiply, subtract these, and we get our answer that calculated to be 2.8. So 2.8 kilojoules of energy. So, and it's positive. So we got this. We got our delta G, our standard change in free energy of the reaction. So now we can plug that into here along with R. Remember, let's remind ourselves R is equal to 8.314 joules per mole Kelvin. Our temperature is 298 Kelvin. So we're now going to plug everything into this equation. So 2.8 kilojoules. Now, the thing we need to remember is R is in terms of joules. So we'll need to convert this to joules. So I'll put that over 1. Use my conversion factor. I know that 1 kilojoule is equal to 1,000 joules. So I'll put 1 kilojoule on the bottom, 1,000 joules on top, and then this is going to be equal to 2.8 times 10 to the third joules of energy. So kilojoules cancels out. So this is our standard free energy change of the reaction in terms of joules. So we'll put 2.8 times 10 to the third joules. And again, just to remind yourself, I'm using this equation now, right? So the joules I calculated here is now going to go put here. So that's what I'm writing here. And then that's going to be equal to negative R 8.314 joules per mole Kelvin. Oops. Multiplied by T, temperature, 298 Kelvin, and then multiplied by ln of K. So now all I need to do is solve this for ln of K. So first thing I'm going to do is divide both sides by this, or I could multiply these together, right? So if I multiply these together, let's see here. Or I could just solve this for ln of K, so let's do that. So here I'll solve ln of K, so let's divide everything. So I'll divide 8.314 joules per mole Kelvin and 298 Kelvin there. And then I'll divide everything by the same over here, negative 8.314 joules per mole Kelvin multiplied by 298 Kelvin here. So all of this is going to cancel out. And then what I'm left with is ln of K equal to this. So I'll rewrite this as ln of K is equal to this. I'll write this as 2.8 times 10 to the third joules over negative 8.314 joules per mole Kelvin multiplied by 298 Kelvin. Okay, so I've got this equal to this. So now all I need to do is calculate this next. So let's go ahead and calculate that out. And when we do, so I should point out that the joules are going to cancel out and Kelvin is going to cancel out. And so I'm left with, moles, I forgot. This is, again, joules per mole. I didn't write the joules per mole here. This is actually joules per mole, FYI, right? So you have joules per mole, joules per mole. Okay, so the moles are going to cancel out here. So now it's unitless because everything cancels out, which would which is what we would expect for K value, because K values are unitless. Okay, so let's go ahead and calculate this out. And when I calculate this out, I get ln of a k is equal to negative, notice the negative there, don't forget the negative, negative 1.13. 1.13. And then to get rid of the natural log, we're going to raise everything, we're going to write everything as a power of e, right? So this we'll write as e, and then this is going to be the power of e, so we're going to write that as ln of k, right? So we're writing this as a power to e because of the natural log. We're undoing the natural log, and this is the way you do it. And so if we do that to one side, we have to do it to the other side. So that means that this is going to be a power of e, 1.13. And so since the e and the natural log as a power cancel each other out, that means that this is going to be k. So k is equal to e to the negative 1.13 power. And all we have to do is just calculate that out on our calculator, and we get k is equal to 0.32. So then this is the equilibrium constant for this reaction here. So that's how you can go about finding the equilibrium constant for a reaction given the tabulated data for your standard free energies of formation and temperature. So I hope this was helpful. If you enjoyed this video, if you learned a lot from this video or anything from this video, then please like the video, share the video. Also hit that like button, subscribe to my channel, make sure you hit that notification bell and click all so you can be notified by me or by me and my videos, all the videos that I put out. And also, last but not least, please put a comment down below. Let me know what you think. Ask me questions, give me suggestions. I would love to hear from you. Thanks for joining me. Have a great day.